We make calculations from the balanced equations resulting from two solutions reacting together, and many students find these quite difficult, but they needn't be. There are various ways to do these, but my way is definitely the best, and this is based on many years of comprehensive scientific evidence being collated. Well, that's absolute rubbish. It's just that my way is the best because I'm making this video and I have the final say. But try them anyway, you be the judge. Right then, we will look at the neutralization reaction between HCl and NaOH, that's hydrochloric acid and sodium hydroxide. A fundamental neutralization reaction, one of the first ones that you would do in fact. Here's the equation. HCl plus NaOH, they react to produce sodium chloride and H2O, water. Here's a titration setup. And why would you be doing a titration? Well, it is to quantitatively find the concentration of a solution whose concentration is unknown, and that would be the sodium hydroxide in the conical flask. And we do this by titrating it with a solution whose concentration you do know, and that would be hydrochloric acid in the burette. The equipment is labelled here, as you can see. So when you do a titration, there are two terms that you definitely need to know. The solution in the burette, we call this the titrant. So again, just a reminder, that's the HCl. This is the solution whose concentration that you know, the known concentration. So the titrant is the known concentration. The solution in the flask is called the analyte, and that is sodium hydroxide. We don't know the concentration of the sodium hydroxide, and it's called analyte. That's quite handy because we analyse it and we want to find out its concentration. But we need a little help to do this, to know when the neutralization point takes place. In other words, to know when all of the sodium hydroxide in the flask has been completely used up or reacted. So we add an indicator that indicates or shows, gives us some way of seeing visibly that there is no more sodium hydroxide left. And one indicator that we use, it's this funny name here. You pronounce it phenolphthalein. Before we do the titration, we add phenolphthalein to the flask containing the sodium hydroxide. Now what happens here is the phenolphthalein changes colour. It changes colour from clear and colourless to quite a vivid colour of pink. So when the pH is way above 7, it's a pink colour. But when that pH of a solution drops to 7 and below, its colour changes to colourless. So what you get is quite a sharp, obvious colour change from pink to colourless. It is a very good indicator because of this sharp change in colour, obvious change in colour, when you have used up the very last bit of sodium hydroxide. So if the two chemicals mix and react together to completion, and if you know the concentration and volume of the known reactant, that's the titrant or HCl in the burette, and if you start with a carefully measured volume of analyte, the sodium hydroxide in the flask, when the reaction is complete, the volume of titrant added to the analyte in the conical flask, it will contain the exact number of moles to use up all of the moles of the sodium hydroxide in the conical flask. I hope you're following this. So how about the reaction between sodium hydroxide solution and hydrochloric acid? Let's write a balanced equation, and here it is. And some data in a table. Now, this is what the data is saying, or the data that we know before we start the reaction. We have 25 cubic centimetres of HCl We also know its concentration. It is 0.5 moles per litre. That's 0.5 moles in every 1000 cubic centimetres. That's the concentration of this solution. And this exact volume has been added from the burette to the flask containing the sodium hydroxide. And it contains the exact number of moles of acid needed to use up all of the sodium hydroxide in the flask. I'll explain a bit further, but without equations, just ratio and proportion, because there is a point to this. Right, again, let me just repeat that. 0.5 moles per litre is 0.5 moles in every 1000 cubic centimetres. Okay, we have already stated that. But let's do a bit of ratio and proportion and say that 0.05 moles will be in 100 cubic centimetres, and take it down a bit further. 0.0125 moles will be in 25 cubic centimetres that we have delivered. Just a quick bit of arithmetic there. We have just worked out the amount of moles, the number of moles that was delivered from the burette. And here it is in a neat table. And from our equation, HCl plus NaOH produce NaCl plus H2O. You see that the number of moles of acid needed is the same as the number of moles of sodium hydroxide present. It's balanced already. It's a 1-to-1 molar ratio. That means that in the 50 cubic centimetre volume of sodium hydroxide in the flask, there are 0.0125 moles of sodium hydroxide. Let's do another table, this time for the sodium hydroxide using this information. So from this data, you can see that the concentration of sodium hydroxide is 0.25 moles per 1000 cubic centimetres, or 0.25 moles per litre. Why? Because if there is 0.0125 moles in 50 cubic centimetres, scale this up by ratio and proportion, that would mean there are 0.025 moles in 100 cubic centimetres. That would mean there are 0.025 moles in 100 cubic centimetres, and therefore 0.25 moles in 1000 cubic centimetres, making a concentration of 0.25 moles per litre. So by ratio and proportion, you have worked out the concentration of sodium hydroxide in moles per litre. We have done all this to emphasise the point of knowing exactly what concentration is, or for you to get used to that. It is a certain number of moles, or an absolute number of moles, in an absolute volume of liquid, usually water. And we have worked out the concentration of the sodium hydroxide in the units that are universally accepted. Not moles in 25 cubic centimetres or moles in 50 cubic centimetres, but you need to express that as moles per litre. When you state the concentration of an acid or an alkali, you express it as moles per litre, and that's what we're doing here. Of course, this is a very long and drawn out way to do it, and that's why instead of this we use the magic triangle. Here you can see it in the diagram here. But it is all important for you to do the ratio and proportion bit first, just to get to grips with it. Otherwise you have no clue what is going on. So this is the quick way to do it using the equation and data. Using the triangle, we can write the following information that you know before we even start the titration. So here's your balanced equation, and here's the mole ratio of the items of interest. So 1 mole of HCl reacts with 1 mole of sodium hydroxide, or NaOH. The volume of sodium hydroxide is known. Before we do the titration, it's 50 cubic centimetres. that's 0.05 litres. The concentration of HCl is also known, that is 0.5 moles per litre. After the volume of HCl has been added to the conical flask to neutralise and use up all of the NaOH in the flask, we find that we have used 25 cubic centimetres of HCl. We can now add this volume to our information under the equation. Now, because you have the volume and concentration of the HCl, you are able to work out how many moles of HCl using the triangle. The triangle says moles equals concentration times volume in litres. That is 0.5 times 0.025, making 0.0125 moles of HCl. We add this underneath HCl and beside N for moles. Now you know that it is a 1-to-1 molar relationship, the HCl and the NaOH that is, so we can now also add 0.0125 under the NaOH. Now you will see that under the NaOH there is a volume in litres and a number of moles, 0.0125 moles. Use the magic triangle again, this time to work out sodium hydroxide's concentration. That of course is concentration equals moles divided by volume in litres, or C equals N divided by V. Another way you should read this is that you have 0.0125 moles in 50 cubic centimetres of solution. So, if you divide 0.0125 by 0.05, you end up with 0.25 moles per litre, and that's the concentration of sodium hydroxide. I hope this makes sense to you, but you can play it 2 or 3 times if that helps. Lastly, and you knew how much acid to add from the burette to know that you have added the exact number of moles of acid to react with an exact number of moles of alkali. Why? Because you used the indicator, which changes from pink to colourless when all of the NaOH is used up. In the next video, I won't go through it this way again, but what I will do is I'll use the magic triangle and the balanced equation with some data, and what we will do is, step by step, work out the concentration, volume and moles in 3 separate reactions. I do hope this helps. Thanks for watching. All for now.